Oops. Hello. Can you hear me? I didn't hear the sound for starting the record. Yeah. Okay. Great. Okay. Let me enable the chat, the public chat. All right. Okay. So welcome back. Today we're gonna finish the part for the matrix chain multiplication problem. Okay. And I think if we have time, we're gonna also wrap up all the whole chapter for dynamic programming. Okay. So last time we stopped here. So for the problem of computing the product of multiplying a chain of matrices, we used this minimal example to show that even if it is a very simple problem, A1 times A2 times A3, it's just 3 matrices and actually it's 2 different ways of putting the parentheses actually have a huge difference in terms of the number or how many scalar multiplications will be needed. Okay, so it's a huge difference here, 10 times bigger if we choose the worst way, right? Which will result in like 10 times greater number of multiplications. Okay, which means you will need for 10 times longer. Okay, and now the problem is a serious one. Like if we have longer chains of multiplications needed, then we better find a way or find the best way to putting parentheses among these matrices being multiplied. So let's state the problem, define the problem more formally. Okay, so let's say we are given a chain that has n matrices, right? And we also, of course, we know the dimensions for each matrix. And we're assuming that these dimensions are compatible with each other. If not, the whole problem is not valid, right? If we cannot multiply 2 adjacent matrices, then the whole problem is pointless, okay? So we assume that the dimensions are known and compatible. So the problem is to find a way to parenthesize the product that minimizes the number of scalar multiplications. Okay? So it's an interesting problem because the possible space to explore solutions is very, very big. It's like if we consider a brute force way, like we simply just enumerate or iterate over all possible parenthesizations, right? We just go through all possible ways of putting parenthesizations and then just try to find the smallest, try to find the best one, the optimal one, okay? So like if we can let the expression capital P of n to be the number of possible parenthesizations for a chain of such a chain of n matrices, right? Then actually what we can find is that this problem has its suboptimal or optimal substructure. Okay, it's another way to say that is in order to solve the original problem, we need to obtain the optimal solution to smaller problems, to sub-problems. Okay, so for example, given this chain that has 10 matrices, okay, so the last layer of parentheses we can put have actually 9 possible positions. Okay, so we can be either between A1 and A2, or A2 and A3, or A3 and A4, or A9 and A10, right? So here I think it's a typo. It should be A9, P of 9 times P of 1. Okay, okay. So this problem, for example, in the case of P1 times P9, this P of 9 is itself a subproblem that needs to be solved as well, right? In this P of 9, it's A2 times A3 until A10. So to solve this subproblem, we should also go through all possible ways to insert the last layer of parentheses, right? Which has 8 possible ways. So if we use a recurrence equation to express P of 10, it'll be like P1 times P9 plus P2 times P8. Okay, so this expression actually is in a more general case. It'll be like this solution can be decomposed into the summation of products, right? If the problem is greater than 2, if there are more than 2 matrices, right? And this k iterates over from 1 to n minus 1, which is all possible ways to insert the parentheses. Okay, so this equation, what we can get is that the solution actually is an exponential function, okay, which is similar to the rod cutting problem, right? If we gonna solve it in a brute force way, which is definitely not the way we're gonna take, right? Because it's simply too just infeasible to go through all solutions. All right, and the optimal solution, or the optimal structure that we observed, apparently indicates that dynamic programming is a possible way to solve this problem. Okay, so let's see what the problem is, what the optimal substructure is. Okay, so now let's create some notations to help formalize the problem. We can use capital A with the indices, with the subscripts I to j. Okay, we use this expression to indicate the results, the resulting matrix from this chain of products. Okay, the starting index, the starting matrix is AI and the ending is AJ. So if it's the product between this range, between AI and AJ, then we can use this A subscript I to J to denote the resulting matrix. That is what we can do. Okay, so again, to parenthesize the products, okay, which means we must split the chain between, we must choose some k, okay, we must choose some integer k, and then we should split the chain between a k and k plus 1, right? No matter what the final solution is, we must choose some place to split the chain, okay? And the results of splitting the chain would be like we have a left subchain from AI to AK and a right subchain from AK plus 1 to AJ. And we can now adopt the same notation, use I to K as the to indicate the left product. Yes, so it indicates that all the matrices are compatible with each other, right? That is our assumption. If there is one incompatible matrix, then the whole thing is not valid. The whole product is not valid. And the A and the right part is from k plus 1 to j. Okay. All right, we have this basically the optimal substructure laid out. Okay, so on the left of the equation, it's the cost for solving the original problem from AI to AJ. On the right, it's basically we decompose the problem into 3 parts. All right, because in order to solve this subtrain, the left subtrain from I to K, we basically need to compute this one, right? For we also need to solve the right chain multiplication, and we need to remember that because the green parts, the red parts is a matrix, and the green part is also a matrix. So if we are going to multiply these two matrices together, there's some additional cost for multiply these two matrices together. Okay, it's a bit like a divide and conquer thought, like we divide the problem into 2 segments, right? But it is not free to do the combining step, right? When we multiply 2 matrices together, there's some work we need to do, okay, which is not constant time. Okay, so if we write it into details, because we know that the dimension of this matrix, the dimension of AIK, this matrix, the dimension of it is pi minus 1 times pk. How do we know that? We only need to look at the 2 ends of the chain. We only need to look at AI and AK, right? Because all the dimensions in the middle, they got crossed out, they got eliminated, right? We know that AI is in the dimension of pi minus 1 times pi, and AK is in the dimension of pk minus 1 times pk, right? And after we have multiplied all these matrices together, those dimensions got eliminated, and the only dimension that's left is the leftmost pi minus 1 and the rightmost pk. That's why the whole dimension for the left product is this one, pi minus 1 times pk, and same thing to the right multiplication. All right, so now remember, we need to consider what is the cost for multiplying these 2 matrices together, okay, which we already know, right? We use the formula P times Q times R, okay, when we have the dimensions from 2 matrices known, right? So in this case, it will be pi minus 1 times pk times pj, okay? All right, so we have this formula written down, then we can further define the optimal substructure, okay? So we suppose that in order to optimally parenthesize the original problem, we need to split the product between AK and a K plus 1. Then within such an optimal solution, the left chain and the right chain, they both need to be optimally parenthesized, right? So we kind of have 2 sub-problems, right? The left problem and the right problem. And then what we can do now is that we can try all possible values of K, because at the beginning, we don't know which K is the best one. So we can try all possible values of K, and then we search for the optimal K, okay? So now let's try to visualize the whole problem using a different framework, okay? So it's actually a convenient way to solve basically any kind of dynamic programming problem. So now what we can do is that we imagine there's some magic procedure or magic function called DP or whatever name you give it. It's a function that knows the optimal solution. It knows the solution to the original problem. And in this case, it will be the minimal number of scalar multiplications for any sequence. Okay, so we can imagine that. So with this magic procedure in our minds, we can apply this function to our original problem, which is A1 to A5, right? So this solution is actually the minimum among such options, right? We can either split the original problem into A1 and A2 to A5, plus the additional cost. Okay, remember the formula we get from the previous slide, 2 slides ago, right? We need to consider this Pi minus 1 times Pk times Pj as the additional cost. Okay, so it should be either this case or the second possible way, which is to solve the solution to A1 times A2 plus the solution from A3 to A4 and the additional cost. So now the additional cost has a slight different term, which is P2, right? It's P1 for the first case, but P2 for the second case, because now the dimension P2 is where we split the problem. All right, so the next case would be the split at between 3 and 4, and the last case would be between A4 and A5. Okay, and that's it. These 4 conditions actually include all the possible ways to, split the problem, right, into different conditions. Okay, and the additional costs are different for each conditions as well. Okay. So now we can do the further split, right? Because DP is a magical function, but in order to decompose the whole thing down to the ground, for example, we should further decompose this subproblem. The subproblem from A2 to A5 also is something we can further decompose, either into the minimum among these 3 options, because there are 3 different places to place the split, right? 1, 2, 3. Okay, so the result would be a similar substructure of the problem. Okay, remember we always need to consider the additional cost. Okay, and we can do the same thing, right? For all the subproblems that needs to be decomposed, right? So one thing we noticed that there is a overlap in the subproblems. When we try to solve these subproblem, we actually solved the subproblem from A3 to A5 already, right? But so ideally, in the dynamic programming algorithm, after we solve the problem, we should immediately save the answer, so that in a later stage, when we come across the same problem again, we can use the table, right? We can use the lookup table to refer to the existing solutions instead of solving the same problems again, okay? And the A4 to A5 is also another example of the same problems. So far at this point, it's a very typical problem that can be solved by dynamic programming. We have the substructures identified, the optimal substructures, and we actually observed a lot of overlapping subproblems, okay, which basically satisfy the conditions of using dynamic programming. Okay, so let's now, in order to write down the solutions, or in order to visualize the solutions, we can use a different framing, like we rewrite what we have so far. Okay, so we have used dp, the magic function dp. Okay, we don't know how to implement it yet, right? We just imagine this is a magic function that knows the solutions. So we apply dp upon a subsegment or a subsequence, subchain. So it's actually not necessary to write those A's, right? We simply need to know where is the starting point and the ending point, right? So we can use the starting subscript and the ending subscript J to indicate where the dp function is applied on. Okay, so we can rewrite the notations from ai to aj to using this simpler form, which is I comma j. Right. So what I'm going to show on this slide is basically the same thing as the previous slide, but I rewrite it with a more compact form. Right. So dp of between 1 and 5 is actually, right, I have d 2 and 5 here, right, because that is from a2 to a5. And all the other 3 cases can also be written in such a more much easier, much simpler form. So what we can further at this point, it's already very a neat form, very neat form. So, but why don't we just use a simpler form, right? We already use a very complex, a very compact form, which is dp, right? So the dp of I and j is actually the same format as this 2D array representation, right? It's no different from a 2D array. So dp of ij is actually the elements I and j within a 2D array. Okay, so it is essentially the same thing. So why not we use the array convention or the array notation to indicate the whole substructure, right? We use M15 to indicate DP15 to replace DP15. So M15 would be the minimum among these 4 conditions. Okay, so you can note that here the whole equation is equivalent to this on the right. The only difference is that we replace the DPs with the M notations, and the meaning of Mij would be that this is the M would be a 2D matrix, and Ij would be the ith row and the j's column elements within that matrix. Okay, so that is the further simplification. Okay, or because it's too much equations, right? Why not we just rewrite the whole thing into a one equation? It'll be the minimum among all possible places to place the k, right? So k can be 1 to 4, right? And the range would be 1 to 1k here, and the k plus 1 to 5 here. And remember, there is an additional cost, which is related to the dimension of the case matrix. Okay, so this is for 1, 5, and then more generally, if the starting if we know the starting index and end index as I and j, we can simply use k to iterate from I to j to iterate over all possible places to place k. Okay. All right, so that's something we obtained eventually. Okay. All right. So now, given this equation, we can come up with a solution very easily. So let's look at a low efficiency recursive solution. Okay. So we will let the elements in the ith row and j's column elements in the matrix in the table M to be the minimum number of scalar multiplications needed to compute the subchain from AI to AJ. Okay, then if the ending index is the same one as the starting matrix, it means that there's no matrix occurred. There's no matrix needed, right? It's just a one matrix. So the Mij would be 0. Okay. So the whole recurrence equation would be like this, right? Consider the smallest case and the larger problems. And actually, this algorithm runs in exponential time if we write it in a recursive way, which is bad as the brute force method, okay? Because the subproblems are solved repeatedly, okay? So we're gonna not go into the details of this low efficient solution, but we'll consider a bottom-up dynamic programming solution first, okay? So the idea is that we don't want to solve the same subproblems repeatedly, right? For each problem, we want to solve them just once, okay? Then we know that from the previous slide, we know that the solution of some problem between I and j actually depends on the solutions to smaller problems, right? So for any k that we choose, the subproblem from I to k or the subproblem from k plus 1 to j are all smaller problems, subproblems of the original problem from I to j, right? So you still remember how we implement the bottom-up dynamic programming algorithm for rod cutting problem, right? In order to know the revenue for longer rods, we need to first know the revenue for shorter rods. Okay, so a bottom-up solution means that we solve the smallest problems first, because the bigger ones gonna be dependent on the smaller ones. And it's actually the same solution here. We want to iterate over all distinct subproblems. Okay, note that it's distinct subproblem. We don't need to, we want to avoid solving the same subproblems. And we will only solve each subproblem just once. Okay, and we will solve the smallest subproblem first. So let's consider the sizes of the subproblem. What is the smallest size of the subproblem? Well, it's not obviously not 1, right? If it's just one matrix, why there's no computation needed. So the smallest subproblem is 2, which means there are 2 matrices in it. Okay. So for the subproblem in size 2, okay, what are the ranges? Okay, like how many subproblems, how many distinct subproblems are there when the subproblem size is 2? Okay, in order to answer that, no, we're not talking about how many subproblems within a subproblem of size 2. It's like for between the range like, for example, in the chain A1 times A2 times A10, how many subproblems are of size 2? Okay, so in order to answer this question, we need to look at A1 times A2. That is one instance. And A2 times A3, right? A3 times A4. And last problem is A9. The last problem is A9 times A10, right? That's what we mean by the subproblems of size 2. Okay, so how do we count that? So obviously in this case it's 9, right? 9 subproblems. So actually you can imagine that it's actually like this. The subproblems are A1, A2 to A2, A3 until AN minus 1, AN, which means the left index I ranges from 1 to n minus 1, right? 1, 2, until AN minus 1. And the right index would be from 2, 3 to n. Okay. So what about larger subproblems? Right, we're increasing the sliding window, right? Right, it would be A1 times A2 times A3, right? That's the first problem. And the second problem would be A2 times A3 times A4, right? So for this L equals 3, we basically let the I, right, ranges from 2 to n minus 2. And the J will be from 3 to n, right? Because the size increases from 2 to n, okay? Anyway, if we summarize it, the more general case, it'll be like, you can imagine a sliding window that has a fixed width L, okay? And you will need to let this sliding window to slide from the leftmost side to the right side, right? And so that we have iterated over all possible instances of subproblems in the size L, okay? So if we have A1, A2, A3, until AN, right? We basically need to first use a sliding window that is of size 2. So that's L equals 2, right? If we imagine we have a window that slides from the left side to the right side, we will cover A1 times A2 and then A2 times A3, right? Until A minus 1 times AN. If we increase the sliding window size from 3, then it will be like a longer window that slide from A1, A2, A3 to A2, A3, A4, and then A3, A4, A5 until the last case, which is AN minus 2, AN minus 1 times AN, right? And this window can be very large until we reach the last subproblem, which is of length n minus 1, right? That is the biggest subproblem, right? So, which is and of course, eventually we want to solve the original problem, which is of size n, right? So we having these sliding windows, this idea of having sliding windows, we can easily arrange all the subproblems in with an increasing order, right? We want to go through the smaller problems first. Okay, so we can basically write a procedure like this, right? So it's a procedure that takes the dimensions as inputs. Okay, the dimension P includes the dimensions for all the n matrices. Okay, so the P0 and P1 is a dimension for A1, right? And the P1, P2 is a dimension for A2, okay? Until we got AN, right? So the P contains all the dimensions. So the algorithm actually store the optimal cost in an array M, okay? And it also store the index, which is the place that we split the problem, okay, into a second array S. Okay, so we have M and S used in this case. All right. So before we look at the major triple layer for loops, we'll look at the first for loop, which is a loop that's over 1 to n, which initialize the M11 MII to 0. So what does MII mean? So MII means that's the smallest case, right? When I equals when the two indices have equal values, which means there's only one matrix. So it's the subproblem that's for the one matrix, right? And of course, there's zero multiplication needed. Okay, so it's an initialization. All right, so next, the outer for loop. Okay, remember we use L to indicate the size of the sliding window. Okay, which is the size for the smaller for the subproblems. Okay, so the sliding window iterates over 2 to n. Right, when L equals n, then it's just the original problem. Right, it covers the window covers the whole chain. Okay, and the second for loop, the I, what is I? I is the left end for the subproblem defined by the sliding window, right? So the I iterates from 1 to this quantity, n minus L plus 1, right? So I has that many possible positions, okay, which is determined by L, right? So the larger window is then fewer options, fewer possible positions for the left end, right? Because your window is very large, so there's less possible ways to slide the window. And of course, the J here is determined by I and L, right? Because the length of the window is L, so you know the left end I, you will know the right J, right? By adding the window length to the left end. Okay, so the first two for loops, this line 5 to line 6 is to go over all possible subproblems. Okay, and the order is that we go through the smaller subproblems. We start from L equals 2. Okay, so within each iteration, we will like initialize a Mij to infinity, and that is something we want to solve. Okay, how do we solve that? Is to use a loop, another loop, which is the loop counter k iterates from the left end to the right end, I to k I to j minus 1, because we want to, given the subproblem from I to j, we want to go through all possible ways to split that subproblem, right? So this subproblem, each possible way to split the subproblem is that the solution is the summation of the left half, which is from I to k, and the right half, which is k plus 1 to j, plus the additional cost, right? The additional cost is how do we, is what we need to multiply two matrices, okay? So this is the same principle as the suboptimal solution, a suboptimal structure that we introduced several slides ago. Okay, so we will only update the values for Mij when we have smaller candidates, right? So Q would be the summation for this cost, because we want to find the optimal solution, which is the way to cut the chain that results in the smallest number of scalar multiplications. Okay, so only when we have Q that is smaller than Mij, then we will copy the Q value of Q to Mij, and also copy the place that we cut the matrix to Sij. Okay, and eventually we will return M and S. Okay, and if we analyze it quickly, it'll be actually big O of n cube, n to the power of 3. And this is expected because we have the problem defined. The algorithm is written in such a triple for loop way, and also that's the scale of the subproblem space. So there's that many distinct subproblems to go through. So it may look terrible, like n cube running time efficiency, but it's already way more efficient than an exponential function method. Remember, if we want to solve the subproblem, if we want to solve the original problem, use brute force way, which means we use a recursive function, then it will be very inefficient. If we compare the running time, it will be a huge difference. So on the next slide, we can go through several examples. Okay. All right, the input chain is from A1 to A4, and the dimensions are given like this, right? Okay, so what we can do is to write a triangle-like tables. It's like we write half of a table and then we rotate it by 45 degrees, right? So this is the area A, area M, in which we store the optimal solutions. And there will be a area S, and S is smaller than M, okay? So this is by definition of the code, okay? So these values, okay, so these values are not pre-filled. They should be empty, but I just didn't make the animation complete, okay? You can think of these are all empty. So first we will need to solve the subproblem of size 2, okay, which is basically these 3 subproblems, okay, from A1 times A2 and A2 times A3 and A3 times A4, okay. And remember, these are the pre-filled zeros, okay, because these indicates the subproblems, the smallest case that don't need to consider, that don't need to compute it at all, right? All right, so following the formula of the within the code that we need to use this formula to compute the cost, right? The first subproblem that we solve is M12. So M12 would be A2 would be 30 times 35 times 15, right? Okay, and of course we need to plus 0 and plus 0, right? But this plus 0 means nothing, right? So we will write it like this. And the way, the only way to place the cut is between 1 and 2. So this one, S1 and 2 would be 1. Okay, so we'll copy the 1 to this place. And for the second subproblem, which is A2 times A3, we do the same computation, right? And for the third subproblem, and then we just copy those. We just fill in the blocks with these numbers that we computed. Okay, so that is the first iteration of the outermost of the outer for loop, which is the window size L equals 2, right? L equals 2 means that we are solving the subproblems of size 2 first. Okay, and the second example, the next step would be solve the subproblems of size 3. Okay, and so for size 3, it requires a little extra computation. Okay, because as for size 3 problem, we need to make comparisons, right? The problem of A1 times A2 times A3, actually, we need to consider 2 options, right? It could be either A1 times A2 times A3, or it should be A1 times A2 parentheses times A3, right? So they correspond to these two conditions. The first condition is M11 plus M23 plus the additional cost. Okay, so it's actually the 0 plus this condition, which results in 7,000 and something. Okay, and the second way would be like M12 plus M33, which be M12 is this number plus 0, okay, plus the additional cost, which would be 18,000. Okay, we need to choose among the smaller, choose between these two. We choose the smallest case. Okay, so apparently it should be this value. So we need to put this value into the cell here, which is M13. Okay, and S13 would be the corresponding place to play of placing the cuts. Okay, right, and similarly for M24, we will compare within 2 possible ways. Okay, and then we will place the solutions within the cells. Lastly, it is the top of the kind of the pyramid. Okay, the last cell corresponds to the original problem, right? Which is size 4. So it's actually 3 conditions, right? We need to compare the 3 conditions determined by where we put the last parenthesis. Okay, so it'll be the smallest among these 3, right? Which we will copy to the cell here. Okay. Okay, so upon this point, we have the problem solved. The optimal solution is 9,375. Okay, though. And we also marked the place to cut along the way, right? We also like marked how do we place the cut? How do we split the parenthesization? So given the M and S return, we are able to actually return the results very quickly. Like the S14, if we look at the top elements, S14, the value is 3. Okay, it indicates that we need to place a parenthesis here. So what about this place? The S, from A1 to A3, how do we place the parenthesis? We simply need to refer a S13. Okay, so S13 is 1, which means we need to place the parenthesis here, right? Indicated by this blue curve, blue arrow. And the last A2 and A3 actually don't need to place further parenthesizations. Okay, so we can use a simple recursive solution to print the recursive algorithm to print the solutions, right? So yeah, so I'm gonna skip this slide real quick. That is the bottom-up dynamic programming approach. And this problem can also have a top-down dynamic programming solution. And basically speaking, any kind of dynamic programming can have two types of solutions. So the top-down method is usually recursive, while the bottom-up ways is more generally non-recursive. So in this top-down solution, each table entry contains a special value that indicates that it has yet to be filled in, right? It's not solved. So when the subproblem is first entered, we need to compute its solution and store into the cell, okay? Each time we encounter the same problem again, we simply look it up and return the value, okay? So this top-down solution usually need to check whether a solution exists at the beginning of the algorithm, okay? So this method is the first part of the top-down implementation. Okay, so it's basically initialize the weight matrix. Okay, and then go through all the possible cells to initialize the cell values to infinity. So it iterates, the J iterates over I to N. So it's basically half of the cells. The other half, they are just duplicates. We don't need to initialize those values. And then we will need to return the lookup chain function with such arguments, because we want to solve the original problem from 1 to N. So the key point is the lookup chain problem, how we define that function. Okay, so it's a lookup chain function, and it's quite, if you compare it with the top-down method of rod cutting problem, it's quite, looks very looks very similar. So the first two conditions is to check whether the problem has been solved yet, right? If it's no longer infinity, we just return it. Okay, and if it's the smallest problem, then we will simply mark it as 0, right? It's already easy to solve. So for the other cases, right, if we want to solve the subproblem that iterates from that defined by I and J, right, we need to look at that many possible ways to place the cuts. So the K will be from I to J minus 1. Okay, so the Q would be the solution of the summation of these three parts, right? The left half, the right half, and then the additional cost. And if the Q is smaller than the current value, then we will mark Q to be the optimal solution. And eventually it will be returned, the MIG will be returned, because the input argument is I and J. Okay, so in order to solve the problem, we need to solve the original problem. We need to simply call the lookup chain on M, P, 1, and N. Okay. All right, that's a straightforward way to implement the top-down method. Okay. So I'll clear the drawings here, and let's look at the last parts. So we have introduced the matrix chain multiplication problem real quick, and we actually have another example that we can talk about, which is the longest common subsequence. Okay, longest common subsequence, which is the abbreviation is LCS, and it's actually a very commonly used method for comparing the similarity between sequences, especially the gene sequences. For example, we have two sequences, X and Y. X are like ABC, BDAB, and Y is like BDC, ABA. So the common sequences are the common parts shared by these X and Y. So in this case, the BCA is of course a subsequence of both X and Y. okay? But it is not the longest, okay? Because we can find longer sequences like BCBA. So in this case, the sequence doesn't need to be contiguous, doesn't need to be like continuous, right? It can be just the sub array or sub parts, but it doesn't need to be continuous arrays. Okay, like BCBA, right? BCBA and BCBA. As long as they are in such an order, as long as the order information is reserved, is preserved, then we can call it a subsequence. So in this case, BCBA is longer, right? So we in the most common case, we want to know what is the longest common subsequence, right? Because the longest common subsequence would be a good indicator of similarity between two sequences. So we will measure the similarity between. This method is usually used to measure the similarity between DNA sequences. Okay, so for example, in these two sequences, the common subsequences are highlighted in different colors here. Okay. So the problem is very straightforward. Okay, given two sequences, X and Y, we wish to find their common subsequence that has a maximum length. Okay, how do we find such a common subsequence? And let's try to build the optimal substructure, which is that we want to find a smaller problem or a subproblem of the original problem. Okay, so in order to find the longest common subsequence between X and Y, right, we can basically like align these two subsequences. Okay, so let's consider the last elements. Simply consider last element, which is xm and yn. Okay, if these two have the same value, if these two are equal, right, which means they will be included in the longest common subsequence, right? Because they are the common parts, right? We can. So if this is the case, then we must find the longest common subsequence of two shorter subsequences, right? Which is from x1 to n minus 1, and the other one is y1 to n minus 1. We exclude xm and the yn because we are sure that they will be included in the LCS. So all we need to focus on is the smaller segments, right? Is the smallest sequence. That is one element ahead of the last elements. Okay. So we can define it as capital X n minus 1 and capital Y n minus 1. And so we can write the kind of the recurrence in like this, because the solution to the original problem can be written as the solution to two smaller subsequences plus 1. So what is plus 1? The plus 1 is the xm and the yn, right? It's one additional element in it, so we need to have a plus 1 here. Okay, so that is the case for the last two elements are identical, are equal. So if not, right, things are more complex. So if not, then we can either shrink the size of y by 1 and look at the longest common subsequences between x and y n minus 1, or we can shrink the size of x by 1 and look at the longest common subsequence between the shrinked x and y, and we choose whichever is longer, right? Because we know that xm and the yn, they are not equal, so they should not be included at the same time to the longest common subsequence. So we can either decrease the x by 1 or y by 1, right? And try to find the longest common subsequence between the altered combinations. But we need to choose the longer one. Okay, so in this case, we rewrite the subproblem into this, equation, which is the maximum option between these two, the LCS of y minus 1 and the LCS of x n minus 1. Okay, and by writing down these two equations, actually we have covered all the cases of the subproblem. Okay, because there's no other cases, right? If we compare the last two elements of two sequences, these are the only conditions, right? Either equal or not equal. Okay. All right, so let's now adopt some technique that we used for the matrix chain multiplication, which is to simplify the equations, right? We can find that all these x, right? All these x, they are like replaceable. We don't necessarily need to use x, right? X and y's. We can use the length to indicate the case, right? It's m and n, and the x m minus 1 would be m minus 1 and the n minus 1, right? And m and minus 1, m minus 1 and n, right? So it's just a rewrite. And further, we simply, because the LCS of I and j is just an entry of a 2D array C, right? We can use an array indicates to replace the LCS. It's just like the DP function that we replaced for the matrix chain multiplication, right? We can replace LCS with the C, and it's the same equation, but written into a 2D array notation. So now it becomes, and also we replace the m and n, right? We'll replace m and n with those I and j's, but it's just equivalent, okay? So this Cij becomes either two cases. If the elements are the same, then we use Ci minus 1, Ji minus 1 plus 1. In other case, it should be in the bigger one among these two cells. All right. So with these equations written down, we can actually write a bottom-up implementation real quick. Okay, so the algorithms is given like this. Actually, we initialize the table to such a memory space that the x and y, the first two dimensions, the two dimensions iterates from 0 to m and 0 to n, okay? Because the zeros are the smallest cases, because a sequence of zero lengths have 0 elements in it, right? So we will let the I and j iterate from smaller cases, so we can like fill out the cells from the smallest subproblem. Okay, so in the body of the for loop, we can find that if either one is 0, then the solution would be 0, because if you are compare the longest, you are trying to find the longest common subsequence between a 0 length sequence and whatever length and whatever the other one is, then the common place must be 0, right? So the 0 is for sure here. So if the last two elements are the same, then we should consider like the cell that is basically the upper left corner of the original cell, because I minus 1 will decrease the height by 1, right? And the j minus 1 will decrease the width by 1. So we are basically referring to the cell that is at the upper left position of the original cell. And remember, we need to plus 1 here. Okay. For other conditions, we need to basically consider the the cells that is to the left of the elements and the cell that is one there's one up above the original cell. Okay, and we made a comparison, then choose the bigger one. And finally, the corner, the right corner, bottom right corner will be returned, because that is the solution for the subsequence of length m and the length n. So this will be part of the homework assignments this time. Okay, a little bit recap of dynamic programming. How do we determine when to use dynamic programming? Okay, so as we mentioned this in one slide, it'll be like, first we want to identify the optimal substructure. Like we say, a problem show the optimal substructure if an optimal solution to the problem actually contains the optimal solutions to the subproblems. Okay, so whenever this condition is satisfied, we can say that the dynamic programming might apply. And the second ingredient is that there's overlapping subproblems, and which means the space of subproblems is like bounded. It should be small. Okay, so a recursive algorithm can visit the same problems repeatedly, and so we can like either implement a top-down method by alternating the recursive algorithms, okay, or we can like determine a bottom-up solution to the original problem. Okay, all right, so that is pretty much for the lecture today. I have released the assignment already. I think you can start working on the dynamic programming problems.